Okay, another property of gases is diffusion and effusion. So let's look at these, define some terms here and think about what we know about gases. So diffusion is the mixing of gases. So the fact that gases diffuse into one another or mix together, forming a homogeneous mixture, we said that's evidence of the fact that they don't form attractions with one another, because they don't separate and stay separated, they mix evenly. It's also evidence that they're in constant motion, because the constant motion and bouncing and collisions is what allows them to eventually randomly fill both containers. So again, this is one of the properties that we can directly observe that gives us strong evidence that the kinetic molecular theory is a reasonable way to describe the behavior of gases. So what this picture is showing is I've got this block here. I've got one gas in one container, another gas in another block. When I turn that, it opens, then the gases diffuse into one another. It's the result of the random motion. Another property of gases is called effusion. It's very similar. It's also a result of the same properties of a gas. Effusion results when I have a gas, instead of mixing with another gas, it's escaping into an empty container. So if in this picture, you got to imagine all the gas was starting on one side, on the left, and this was a vacuum over here, and there's a small hole in between, and so then the gas effuses into the vacuum. Again, due to the random motion and the fact that the gas particles don't attract, they just randomly bounce around. Once in a while, one flies through the hole and it goes into the vacuum. Graham's law allows us to say something about how quickly diffusion and effusion will occur. So it governs both of those properties. And it says if you're at a certain temperature, the rate of gas is mixing together, or the rate of a gas effusing through a hole into a vacuum is proportional to, or inversely proportional to, the square root of the mass of the gas. Right, so in words, if we wanted to describe this relationship, we could say if two gases are at the same temperature, the lighter gas, the one that's less heavy, will be moving at a faster speed, and so it will mix with other gases faster. It will be able to travel through a hole and diffuse into a vacuum quicker. So the rate of diffusion and effusion is faster for lighter gases. And it's just a way of quantifying that relationship. Does the temperature impact the rate of diffusion and effusion? Absolutely, yes. So really, ultimately, what we want to say is at a higher temperature, we have more kinetic energy on average, so the speed increases, and so the diffusion and effusion are faster. We can also say if the temperature is constant, then we look also at the mass, because if we have lighter mass or less mass, we have a faster speed, and so we have faster rates of diffusion and effusion. Ultimately, the rate of diffusion and effusion is determined directly by the individual speed of the particles. So what speeds up the particles? A higher temperature or having a lighter mass. And that's what makes them effuse or diffuse faster. And so there's an interesting experiment before we talk about gas pressure we can mention that illustrates that. Here. So I want to turn down the volume. Take a look at
a direct demonstration of
okay,
gaseous
so here we have ammonia
is provided by diffusion,
HCl.
the gradual mixing of molecules of one
and we're
gas
take
with
samples
molecules
of
another gas.
and we're going to
In
put
the
them
apparatus shown, an
into the
aqueous
ends of
ammonia
this
solution is
tube.
injected in the left side of the tube.
Okay, so what's happening here is actually, let me just go back. Okay, the ammonia is on the left, the HCl is on the right.
Ammonia solution is injected in the left side of the tube.
Okay, so ammonia and HCl vaporize readily. They are not, in their pure states, they don't have strong enough attractions to hold the particles close together. So they evaporate easily and become gases. So what I'm effectively doing here is adding ammonia gas and HCl gas. There's also a reaction that these will undergo when they meet. The ammonia, chemically, if we look at the structure of that molecule, being trigonal pyramidal gives it some polarity. It's partial negative on the top. And the HCl has a big electronegativity difference between hydrogen and chlorine. So there's a big partial positive here. And if these two collide with enough energy, the electrons from the nitrogen can start to be shared with the hydrogen, and it can grab the hydrogen from the chlorine. If it grabs the hydrogen, it will produce now a new molecule. So this is a chemical change because I'm changing the way that the electrons are arranged around the atoms. When I do this chemical reaction, now I get ions. So now I've got charges that are opposite, and they will attract. So what can we predict is going to happen as these gases travel through this empty tube? When they start to meet up, as they're traveling through here, they're moving fast, they start to collide, as they start to meet up, they're going to form into these ions. And since ions have large charges, they're not going to stay in the gas phase. You don't usually see fully charged particles flying around in the gas phase, because a fully charged particle, when it comes even with a strong collision to another fully charged particle, those full charges are a strong attraction and they stick together and form ionic bonds. So what we're going to see here is the formation of a solid somewhere in this tube that results from these ions forming as the NH3 and the HCl meet up, exchange a hydrogen, and start to form the solid. So the question is, where on the tube is the solid going to start forming? Is it going to start forming closer to the HCl, or is it going to start forming closer to the NH3, or is it going to start forming right in the middle? How do I answer that? Yeah, except the HCl is the heavier one. Right. So what he's saying is, this is an experiment that's testing the rate of diffusion, the rate of mixing of gases, the rate of gases moving through space. So if I look at the masses, if I take the mass of 1 nitrogen and 3 hydrogens, I get a mass of about 17 AMU. And HCl, which is chlorine, which has a mass of about 35, plus hydrogen, so it's about 36 AMU. This one's a lot heavier. So the HCl is not going to travel through this tube as fast as the NH3 will. So we can use that formula that we saw to actually calculate how much faster the NH3 will be moving than the HCl, and calculate exactly where the solid will start to form due to the differences in speeds as they're moving through the sample. So,
and at the same time, aqueous
once those
hydrochloric
gases are in
acid
there,
is injected on the right side.
they start to
Ammonia
evaporate,
gas
the
diffuses from
vapors
the
move
left,
through
and
the
hydrogen
through the
chloride
tube
gas diffuses from
at
the
different
right.
rates. They're
two
at the same
gases combine to
temperature,
form
but they don't
ammonium
have the same
chloride, a
speed.
white
They have the
solid.
same average kinetic energy,
Note
but the
that the
heavier one
ammonium
needs to be
chloride
moving
forms
slower,
nearer to the
and I
right
start
side
to
where
see
the
the formation
hydrochloric
of the
acid
solid
was injected.
right where I expected.
We zoom in
Closer
to show
the
the
heavier
reaction
one
on a
because
molecular level.
when they're at the same
In
kinetic energy,
1832,
the
the
heavier
Scottish
one needs to
chemist
have
Thomas Graham
a
found that
slower
under the
speed
same
in order
conditions
to
of
give it the
temperature
same
and
kinetic
pressure,
energy as the lighter
rates
one.
of
And then
diffusion
this
for
is
gases
showing
are
the formation
inversely
of the
proportional
solid
to the
as a
square
result
roots
that
of their
hydrogen
molar
being
masses.
transferred.
This statement, now known as
once the
Graham's
hydrogen
law
is
of
transferred, they
diffusion, is
create
expressed
charges and the charges
mathematically
attract.
as R1 over
I don't like the
R2
fact
equals
that
the
once
square
the
root of
charges
M2
attract,
over M1, where R1 and R2 are the diffusion rates of gases 1 and 2, and M1 and M2 are their molar masses respectively. Because ammonia is lighter, it will diffuse faster than hydrogen chloride.